Right. So now that you have had a good impression of SPARQL, of its data model and of its syntax, and also of modeling in this graph-based format, it is time to take a glance at SPARQL. SPARQL, that's the query language that is most widely used for RDF, and it is the key technology to actually get something out of RDF data once it's stored in a graph. My name is Markus Krutsch. Thanks for joining again here in this little video series on knowledge graphs. Right, so let's go straight into the material in this short video. SPARQL, as I said, is a query language, but it's actually more than that. It is a W3C standard which has several parts that are not just about querying. The abbreviation itself stands for SPARQL Protocol and RDF Query Language, a recursive acronym that gives rise to this attractive name. It has been around since 2008, which is a striking historical fact since, as you know, RDF has already been around since 1999. So in some way, people managed to store data in RDF for almost 10 years without being able to query it, at least not in a standard way. But you also might know that the tin opener has been invented only many years after tins had been invented to preserve food. So it's a bit like this. It has also been updated in 2013 to something called SPARQL 1.1. And when we say SPARQL today, usually this is what we mean. The old SPARQL is only of historical interest. Tools that support SPARQL 1.1. And there are a lot of these tools. Many graph databases have implemented support for this query language, and also there are several free libraries that one can use to implement support with a medium amount of effort, I would say, given how complicated and feature-rich this language is overall. Now, as I said, it's more than just a query language. Also, querying clearly is an important part here. But it also defines result formats. So it tells tools how to obtain results from a query. And it turns out that the formats used there are not RDF in most cases. So SPARQL queries, as we will see, do not return RDF graphs. They return something which is rather similar to database tables. And to encode these tables in a machine readable way that can be interchanged between applications, there are several formats as part of the standard. There's also an update language. You may know this from other query languages such as SQL. They can not only be used in most cases to get data out of the database, but you can also issue queries to write data. And this makes sense to be combined because often you want to write data based on certain query criteria. Yeah, you could say for every person in my database who has a certain property, you would also like to add another property. So this requires first querying because you need to find the right parts of the data and then update in order to do the modifications. So having this in one formalism makes a lot of sense. There's furthermore protocols for communicating with online services. I was already saying for RDF, and you have seen it with the IRIs and other aspects of this language, that the web has always been a big factor in defining these technologies. Of course, that has something to do with the W3C doing this. And as such, also for SPARQL, the question of how to call a SPARQL engine remotely, how to offer a web service that implements this, was also important and has been solved. And finally, there's even a vocabulary to describe such services if you want to publish them in a machine-readable format. Okay, all of these specifications can be found online and are publicly available as usual with these standards. If you haven't done so, I really urge you to take a look at some of these documents. We have seen that for RDF as well. There are the original specifications online, and of course you can watch videos like this one or read lecture notes or go to some textbooks. But in the end, it's always good to know where the original primary sources are and to have a look at them to understand whether they are useful for you or whether you would rather prefer to have secondary literature on this topic. But for some cases, actually just looking up the standard is the easiest way to get a solution, and it's not that difficult to find your way around there. Okay, so let's look at SPARQL queries. Let's do that by example in this little video. This particular SPARQL query that I'm showing you here is a SPARQL query that does something very simple. It asks for a list of all resource IRIs together with their labels, where the label is given by this standard RDFS label property that I had been mentioning before. What do we see here? Well, there's a prefix declaration that shouldn't come as a surprise. You know that from Turtle. It's a way to abbreviate lengthy IRIs and to make this all more usable. There's a select part. Select, that's the keyword used to specify what you want to have in your result. This idea should be familiar to you if you know SQL, even though the similarity is rather superficial, one has to say, but the keywords are often the same. And in this case, select lists two things, resource and label, both with a question mark in front. That means that these are variables. So they are things that can take different values, and we would like to have the values for both of them. And then comes where that is the actual query condition. And in this case, the query condition is simply a single line which encodes a triple, or rather a triple pattern, I should say. It looks very similar to the syntax that you know from Turtle again. But now we have variables inside what would be the triple. So the subject here is the variable resource. The predicate is the RDFS label property abbreviated with the prefix. And the object again is a variable, in this case label. And what this does now is it retrieves all the triples that match this pattern, where you have some resource connected by RDFS label to some label. And you want to get for these things the resource and the label. So summing up the main things we see here, first of all, is that SPARQL uses variables. That might be seem obvious at some point because it is a query language. But if you think of SQL, for example, you see that the use of variables there, this is very different notion of doing it. So usually when you want to get a value from SQL, you would have to address this as by taking or specifying the column for a certain table, and that will give you the value which is in a certain column in a certain table. So the variables in SQL represent whole rows, so to speak, with all their column values. Whereas here, variables represent really explicitly individual nodes in the graph and possibly also individual properties in the graph. Also not in this example. Yeah? They are marked by a question mark. That should be easy to remember. The core is the query condition, as I said. Things look very much like Turtle, both regarding these prefixes and the way we write the conditions. And indeed, the key idea here in SPARQL is that in order to query for something, you write a little graph, you specify a little graph pattern that looks like the thing that you are looking for. So it's almost query by example, one could say, on this level. We are specifying here a triple, which we could also give more triples, and it would be a little graph. Here it's like a graph of a single triple. And what this means is that we are looking for all graphs that are occurring in the data which look similar to this graph, where something is connected with RDFS label to something else. So it's like providing an example, but replacing certain pieces with placeholders. Very direct form of querying. You write down what you are looking for, and it fills in the missing pieces. And well, the important keyword here is select, where we specify what should be the result. And in this case, the result would really be a table with two columns that specify the possible bindings for resource and label. So for every match of this pattern here, you would get one row in this result table. Okay. So this is a query, and on the next few slides, I want to show you a few more queries, again, to give you a bit of a feeling of how SPARQL looks, and to show you some examples without going into any details yet. Okay, so here's one which finds up to 10 people whose daughter is a professor, using makeshift vocabulary with some suggestive meaning, obviously. So I use a prefix here, e.g. for the example, just to make the IRIs shorter. I want to select the parent, so that's the person with the daughter. And the parent is occurring in this pattern here. It should have a has-daughter relationship to something which we call child. And here you see for the first time a variable which does not appear in select can also be used in the pattern that we have here if we need some more unknown nodes that we would like to refer to. And in this case, we use this child to then refer to the same node again here and specify that it should have the occupation professor. Again, making up some identifiers for these concepts. And there's a limit 10 after this, meaning that there should be up to 10 hits for this query and not more. Again, this should be fairly intuitive and also similar to other query languages you might know. Okay. This example shows a very basic type of query that uses aggregates, in this case counting. Aggregates in query languages are means to sum up results. So instead of returning a whole table with many rows, we return something which sums up several rows in the table into one result. In this case, we actually have a huge table, because if you look at the pattern here, it just says variable subject, variable predicate, variable object. So this pattern matches every triple. So the table we would return here has every triple in it as a row. But what we return actually is not this table, but rather we just count the rows in this table. We count the results. And to do this, we use this function count star, count everything. And we want to return this function and give it a name count. So we return this as count. Everything in the result has to have some name. And if it's not something which comes from a variable inside the pattern, it can be a function value like the one of count here assigned to a new variable name that we only give here. I could also call this differently, could call this number or whatever, triple number. But this count here, this is a built-in aggregate function of SPARQL, and it has a fixed name, and I should not change it, otherwise it will not work anymore. Okay, so this is how we count all the triples in a database. And it's an interesting query to ask. If you ever come across a SPARQL endpoint, that's maybe one of the first things you want to do out of curiosity, how to find out how big is this database. And of course, in practice, tools will not do this by first computing this large table and then counting, but they have much more efficient ways of getting this number. So it's usually safe to ask this query. It will not bring down the server. Right. What else can we count? Well, it's also possible to count just some aspects. For example, we may only be interested how many different predicates are used in the database. Yeah. So even if you have a large database, it could be that it uses only 3 different predicates to encode 3 different relationships between the things in this database. And if you want to count such a thing, you would use the same pattern, because we want to take all triples into account: subject, predicate, object. But the result we return now as count is just the result of counting distinct predicates. And there's an interesting thing here. So first of all, we count predicates. This is what is expected, because this is what we wanted to do. But we have the distinct here, which tells us that we should only count distinct predicates, meaning we should not take duplicates into account. So if the same predicate occurs multiple times in the result, it should not be counted multiple times. And you can see that this could, of course, happen. If many triples use the same predicate, then this predicate would appear many times in the output table. In general, SPARQL, like many database query languages, adopts a adopts a multi-set based semantics, so a back semantics, meaning that results can, the exact same result can appear multiple times in a query result. It's not automatically removing duplicates if it's not stated explicitly. Okay, so this is some examples of aggregates. We could also do other things, but for now this should suffice. Here's another query which shows some further capabilities. So person with most friends. So we want to find who has most friends, at least digitally. For this, we select the person and something which we call friend count, which is the count of all the rows. But in this case, since we have person here, with person here on the sides, it will behave somewhat differently. So the pattern we have is person has friend, and I'm now on purpose am not using a prefix, but really specifies a whole IRI, which is also possible, just the same as it would be in Turtle. So we are looking for triples which define that a person has a friend, and we now group these results by person. So this you can think of as cutting the result table, which returns all the matches for these two variables, into many small tables that are each for one of the persons occurring in the result. So for each person in the result, we have one small result table, and this is the grouping effect here. And the aggregation here will then apply to these small tables. So in the selection, we will return the results for one such grouped table. And each such table has a unique person because that's what we group by. It will always be the same for all rows here. And it has a certain size of or number of rows, and this is what we get by count star. So this query here returns for each person the number of friends that this person has in the database. But that's not enough to find the person with most friends. To get this, we additionally sort the results in descending order by friend count, meaning that the highest friend count will be at the top position, or the maximal friend count. If several people have the same number of friends, of course, only one will be on top. And then we add limit 1, meaning that only one of the results, only the first row will be emitted. And this means that we will obtain the person who has most friends, or let's say a person with a maximal number of friends. If all the people have the same number of friends, we will still get only one here. Okay. Right, so this is a more advanced usage of count with grouping involved. Again, if you have seen other query languages such as SQL, then these ideas will not be completely new and alien to you, but will hopefully make sense. Okay, and here's one more before I conclude. So what we want to do here is to find pairs of siblings. I want to select child 1 and child 2, the two siblings, where parent, some parent, has child 1, and child 2. So what I'm using here is an abbreviation from Turtle that you have learned about earlier. If we put a comma instead of a full stop after a triple, it means that the next triple uses the same subject and predicate. So we are asking for parent having child 1 and parent having child 2. And these are the results. Okay, so this gives us all pairs of siblings. Or does it? Yeah, well, it definitely gives us all pairs of siblings, but it's actually not the query we want to ask. So maybe if you don't see it immediately, you could pause the video and think about it for a moment. Okay, so what's wrong with that query? Right, so the problem, of course, is that other than having different variable names here, there's nothing in the query that requires that the placeholder used for child 1 and the placeholder used for child 2 should be distinct. And indeed, it is not the case in SPARQL that every node in a query result is only allowed to be used as a value for one variable. It could well be that a parent has only a single child, but we still can find a solution to this pattern by simply mapping child 1 and child 2 both to the same single child. So we would have solutions here where child 1 and child 2 are matched to the same. This is something that SPARQL always allows. If we don't want this, we can simply say so. And to do this, we would use what SPARQL calls a filter. And in this case, the filter is very simple. We would just say that child 1 is unequal to child 2. And this would require that only solutions where this is satisfied, where this is true, will be returned. One can still wonder whether this is the best way to phrase this query, because you can see that there are other problems happening now, right? If two siblings exist in the database, they will appear twice here. If there's more siblings that are all mutual siblings, so if a parent has more than 2 children, there will be even more additional outputs. Also, this might be desired in this case. They are all mutual siblings, but maybe we should use a smaller or strictly smaller sign here to say child 1 is the one which is by some order strictly smaller. And actually SPARQL supports that. In SPARQL, even IRIs, even these abstract identifiers, have some implicit order, and one could use that in the query. So if I put a strictly smaller or a strictly greater here, I will make sure that every pair of siblings appears only once in this query result and not twice in both permutations. Okay. So these were a lot of example queries, and I hope that they give you a basic feeling of how SPARQL works. Essentially, we specify a pattern which looks like a graph using a syntax that we already used for writing RDF graphs, namely turtle, with the only difference that there are variables in the pattern now, and these are the results that we would like to see in the query answer in the end. Okay. There are many, many more features which I have not even touched here. They will be discussed in later videos, don't worry. So for now, let us just observe what the structure of SPARQL queries is, because this we can already deduce from these examples. Essentially, we have several major blocks which appear always in the same order. There's a prologue, which contains things like prefix and base, same as in turtle. It comes as the first part of the query. There's a select clause. In all the queries we have seen, this was what was used, select. And there could be possibly other keywords such as distinct. And then after select, you can either use a star if you just want to return the values of all the variables that appear in your pattern, or you can specify a list of variables and variable assignments. And we have seen both in the example. Variables are just the names of the variables with the question mark. Variable assignments are things where you have a function like the aggregate function count star, and you write as a keyword to assign the value to count. Then there comes a where clause, which gives the actual query condition. And finally, we have what is called solution set modifiers, such as limit and order by. Okay. There's more possibilities to write SPARQL queries. There's other types of queries, first of all, which don't use the select keyword, but use another keyword in its place. There's ask, for example, which just checks whether there would be at least one answer. So it's a way to check if a select query would have results without getting all the results. Somewhat similar to running it with limit 1 and ignoring the actual bindings, maybe. But returning essentially just true or false. And then there are two specific things which are used to not return tables, but rather to construct RDF graphs. So it is possible to return results in RDF. And the construct query does so by applying some kind of template, which is again a little graph pattern to each of the results. So it is like taking every result in your result table, every row, and using it to instantiate a little RDF pattern. And then the result is the overall result is the graph that you get by taking the union of all of these instantiated patterns. And describe is somewhat implementation specific, which is meant to provide you with RDF information about the query results. And what this information will be depends on the application and the choice of the people who have configured or implemented it. Okay, right. So with this, we end this little video. We have seen a first quick we can't see a glance. We have taken a first glance at SPARQL as a query language by examples, and I hope that these seemed fairly intuitive to you so far. We will have many more SPARQL queries. At this point, let me also mention that if you are just watching these videos, you are only getting half of the course. There is a lot of material in problem sheets that we offer on the side of these videos, which are discussed in exercise classes at the university, but which you can also look at for yourself to check what you have learned and test your knowledge. And I will link these in the video descriptions usually so that you can find the matching problem sheets. And many examples of specific SPARQL queries and many tasks that you can solve with SPARQL are actually found in these problem sheets, where you can do things much more hands-on. I think for many things that you want to learn in this course, this is a better mode of learning, simply because they are very practical, and by doing it, it's just much easier to get a feeling for how this technology works and what you can do with it. This will also be something that we will continue to do in these videos. In the next video, I will still look a bit closer at SPARQL. We will discuss in somewhat more detail how basic graph patterns, the simple patterns that I have used in my SPARQL queries so far, work, and how the answers there are defined. But after that, we will continue to look into a practical example of a big knowledge graph where we can actually apply this knowledge to get some interesting query results, namely Wikidata. Okay, so thank you for watching, and see you in the next video. Bye-bye.